Swayam Prabha. Digital India. Educated India.
Doing the kinematics of rigid bodies. And in that, we classified the 2D motions and 3D motions as translation and then rotation. So that some of these two will lead to general motion, or even the other way also. Any general motion can be split up as a translation and a rotation, which occur simultaneously. And then we have derived the equation. So I'm just putting down the basic equation. This is in contrast to the absolute motion analysis. For example, there are some simple cases of just a rod having some simple motion at the two ends. So they can be related by some parametric equations or some closed form solutions. And then you can always differentiate it to get velocity relationship. And you can also differentiate it twice to get the acceleration relationship. So that's possible. We did one example of a rod moving whose ends are moving in a horizontal and vertical motion. So the rod keeps sliding. So if you want to relate these two, then since we know the motion of A and motion of B as horizontal and vertical, so and then we related these two by some simple relations. So something like you could have started as x square plus y square is equal to L square, and then you can definitely differentiate it twice, once and twice to get velocity and acceleration relation. So those things are good, elegant, only for some simple cases. So whereas we are seeing the second approach where we use a more generalized approach where particularly this is suitable when you have a lot of connected bodies. So you go from, for example, the usual example we take is a crank. So interestingly, this has a connection of 3 bodies, or may even be 4 bodies. One crank and a second connecting rod and a slider here. And then we also say that the whole body here, the ground, is also a link. So leave it. So it's actually it's a 4 rigid body interconnected. So in this, so we have essentially, in this particular case, we are interested in how 1 and 2 are connected, so that while this has a circular motion, so this is going to have a rectilinear motion. And then obviously there are velocities and also there will be accelerations. So this particular concept here of relative motion of 2 points on a body. This is a single body in which AB are 2 points and the distance remains constant. So using all that, so we have derived so that the velocity of V and velocity of A, and then velocity of B with respect to A. So this is very neatly written. And here, so this is, that means that if you just take this first part, we say that the points B and A are having same velocity, which is equivalent to translational part. So if you take this part, so this is the rotational part. So we can even continue to write this relationship as this is a rotational part. So which means that we can write it as omega k. Omega is the magnitude and k is the angular velocity direction. So we assume that if it is counterclockwise, it is positive, and then clockwise is negative. And then there is a position vector B with respect to A. So this is a vectorial relationship, which can also be converted to I and J relationship. That's also equally possible. And so this is equivalent to two scalar equations. So if you look at the vectorial relationship between these two, so we have, if you think that velocity of A is like this, here, so we'll start with an origin here. So velocity of A is represented here, and on which when we multiply this omega versus RBA, so you know very well if there is an angular velocity here, and then if it is taken, this is RBA is a vector in the direction of AB. So that's B with respect to A. So that means that we join A to B. And then if you do it, obviously you know what it is. So you know that if that is, this is only B rotating about A, without any knowledge that A is also moving. So this is only a relative motion term. So that means that if you think that A is fixed and B is rotating, so obviously B will be having some motion perpendicular to this one, either this way or this way, but this relative velocity component has to be perpendicular to AB. So you can draw it. So this is, and then the resultant, so the addition of these two will give you, okay? So you can very well see that vectorially we can represent it. So the velocity of A in this direction, and then add velocity of B with respect to A, and magnitude is it's omega times RBA, and the length. And then if you add it vectorially, the one you get is the velocity of B with respect to A. So this is basically a relationship in the vector direction. Okay, we will see more examples, given specific examples, how we can write these vectors in terms of ij components. So we can continue to do, yeah.
The left side one is not V of B with respect to A, it is V of B, no sir.
The left side term, say it again.
Sir, in the triangle, you wrote V of B with respect to A twice. The left side one is V of B, that's it.
Velocity of B with respect to A, because this is velocity of A, to which we add velocity of B with respect to A, and together with this, these two added together will give you velocity of B. So that's supposed to be, okay, supposed to be representing this one. Okay, you will understand
Sir, left
this.
side one you wrote V of B with respect to A. It is not V of B with respect to A. It is V of B in ground state, no sir.
Sir, in the triangular figure.
Yeah. Oh, I'm sorry. Yeah. Thank you. Yeah. You're right. Yeah. So it's more VB. Yeah, it's not VB with respect to A. So thanks. Yeah. So this is what it is. So this we can also continue to write, interestingly, acceleration relationships. So in the acceleration relationships, so if you continue this, if you continue with the acceleration relationships, so we will write AB, AA, and B with A. So here, this B with A may have two components. So it's a motion of B around A, which may give you two components. The normal component, say N, or just simply say N here, and B with A, the tangential component. So why is this normal component? So if you have an angular velocity, so it is going to go in the direction of B to A. So if B is rotating about A, so this B will have a circular motion. So, and it will give rise to two acceleration components. One component is centripetal acceleration starting from B to A, and the other one will be the tangential component. So maybe we can simplify it to some extent. You know, the normal components is omega squared times RBA. And here I will still leave it. So I cannot, this is essentially in the tangential direction. So this whole thing can be, say, if you have some acceleration here, and to which we have to add acceleration of B with respect to A. One is the normal component. I know it's going to go down. So this is the origin here, and this is the acceleration of A, to which we have to add this one. So which is in the direction of radial direction, starting from B to A, and so this is the normal component, which we write as, okay, and then to which we add the tangential component, so which may be like this. I'm not really knowing any magnitudes, but then I'm just showing the directions. So we'll come to it actually when you take up a particular problem. So the magnitude is alpha times RBA, okay, the distance, and then this is perpendicular to, so this is in the direction of AB. And whereas this is perpendicular to AB. So whether it is this way or this way depends upon the angular acceleration. So if you add these two components, so then adding this toe to tip, and so this will give you the final acceleration. Okay, so this is basically the equation, and then how it translates into a diagrammatic form, and this is a thing. So maybe you can, so that means that the acceleration of A is like this, and acceleration of B is like this. Okay, so that is okay. I hope you can follow it up. And then this is going from A to B. As I was explaining this problem here, the crank and connecting rod problem. So crank, one end we know, so the other end B we know to some extent. So B is connected to AB, BC, and then BC is another body, and we can relate this kind of equation. And then finally we know what is the slider, some information about the motion of the slider. So now let's look at how we can explain these things in relation to some examples. So let's take some simple examples. Yeah, so let's look at some simple example. This is a simple example where we have a rod AB of length L and which is sliding in the horizontal and vertical slides. Let's say the length and maybe some instantaneous position, the theta. In fact, these relationships are, though the vectorial relationship is general, but a particular vectorial diagram is obviously going to depend upon the directions. So the directions obviously is the instantaneous position. So this theta may be now like this, and as the motion proceeds, so theta may change from 60 to 75 or so something like that. So remember, so this relationship is the instantaneous relationship at that particular instant. So now let's try to analyze this one. So if they say the velocity of this A is given, if the length and theta are given to us, so if are given, can we find B? Okay. So what we know here, interestingly, is that B, you can only usefully use that relationship when we know the information about the motion of those points. For example, there are some examples will come later. An extended rod. So you have a hinge, a slider here. On the slider, B is moving, and then you also have an extension of this rod. So between A and C, if you want to, if somebody asks you what is, say, VC, what is VC, what is the velocity of C, you cannot directly go from A to C. Though we know the velocity of A, you cannot directly go to C because, why? Because in this relationship, which we write so here, what is needed if you want to find out the velocity of B? So you have to know velocity of A, and we have to know the velocity of omega. Okay. So however, so since this is a vector equation, so we will be able to solve for two unknowns. This is a vector equation which is equivalent to two scalar equations. So in this equation, in the two equations, so you can solve for two unknowns. So what is that which we can solve here? So the thing which we can solve here, what is that? So we know the velocity of A. As far as the velocity of B is concerned, so we know it is vertically up. So that means that we can solve for the velocity of B and omega. Okay, velocity of B as well as omega, right? Using that, so if you want, then you can go for velocity of C as velocity of A plus velocity of C with A. And this is again so we cannot directly go to this relationship unless we solve for omega. So omega is here, omega is necessary. So omega can be solved only from this equation, because if you write down this one, so you can write it down in terms of say I and j, so it's VBJ, and we know that VAI and omega k cross B with A. So at a particular instant, we have it at theta, and B with A, you can write it as L cos theta I cap J. Okay. So we can continue. Right?
Yes. VB equal to VA plus, right? So VB equal to VA plus omega k bar cross.
Omega k, I'm sorry, plus. Thanks. Yeah. Here also, it's not plus. Thanks. Yeah, good. You're following it so attentively. So this is, so we can continue to do this one. So it is omega L cos theta J and minus omega L sin theta I. So you can, so what is that which we have used? What we have used is that we know that the velocity of A is in the horizontal direction. Okay, so that's why we used only VAI. So similarly, we also know the information about B. We have some constraint that B is moving in the vertical slide. Okay, vertical group. So we also know that VB is only in the vertical direction. So these two are important. Okay, so whereas if you simultaneously, I'm also doing this one. So if you want to do this one, so here, what is that which we know? We do not know the velocity of C, the direction, nor the magnitude. And here, if you want to directly come to this relationship, so velocity of C has two unknowns, and there's also an unknown of omega. So this cannot be solved, okay, if you straight away try to come to this equation. No. So before that, we have to relate those 2 point motions where we know some information about the motion. Okay. So here, first of all, we have to relate A and B, and this is how we have done. So this can be solved as, say, the equation in I component is 0, and we have VA and omega L sin theta, and BB here is nothing but omega L cos theta, right? And from the first one, we can get omega is VA by L sin theta, and from the second one, we can now substitute that omega here, and it's simply VA by L sin theta times L cos theta. L gets cancelled. Okay, so it is VB L cos theta by L sin theta. So this is how you can solve this first part of the equation. After that, if you want to know the motion of C, the velocity of C, then we can come to this one, and then you can even solve for BC. So I'll leave that part to you, but this is what you should do. So this is VB, and also we can do it in a vectorial form. So simultaneously, I'll also keep doing the vectorial representations. So the vectorial representation is, so we have VA like this, right? And then now I want to write B with respect to A. So keeping this A, so then B will be moving in this direction. Okay, so B will be moving. So this is the direction of VB with respect to A. It may be going up or down. So we do not, at this instant, I do not know. But what is that? It should be either down or up, so that the velocity of B will be vertical. So that means that I have to do that here. So something like this one, right? So this is the velocity of B with respect to A, and And then when I add these two, the velocity of B should be vertical. So that's only possible if you take a point here. So this is the velocity of B, and this is the velocity of B with respect to A, and vectorially. So this is how it is. In fact, the geometry using this is theta. And what is theta here? So theta here, so that's between horizontal and L. So then this will be vertical and L. This is because this is horizontal, so that velocity is vertical to this one. So this is theta, and if you want, this also is theta. Okay, so in fact here, so if you know VA, you can calculate VBA or even VB. So if directly, so if I know VA, so it is VA by VB. VA by VB is tan theta, or VB is VA cot theta. That's what it is here, right? So in fact, instead of going through all this one, so if you are good at drawing these figures and getting the relationship, that is the best. Okay, I always, in the tutorial also, I'm going to insist that not only you do this, but also do by vectorial representation. Okay, so that's what it is. In fact, this VBA, what is the magnitude then? So if this is given, so that is nothing but VA by sine theta. So you can see that VBA magnitude is, if VA is given, then it is nothing but VA by. What is omega then? So VBA is nothing but your L omega. So that means that omega is VA by L sine theta. So then what is the direction here? Earlier we got omega. Okay, omega, we got a positive quantity. That means that it's a counterclockwise, right? We didn't get a negative quantity. So here, how do we decide whether it is clockwise or counterclockwise? How do we decide whether it's clockwise or counterclockwise? Because this is vectorial, the way we got it from drawing the vector diagram. So we can see that, so the way of the sense of omega is that the VBA is in this direction. So that means that what is VBA? You are holding A, and VBA is not like this. So it is, VBA is upwards like this. So you can see from the diagram. So if it is holding A fixed, this is going like this. So that means that it is a counterclockwise. So from this sense, so omega is counterclockwise. Okay, so this is how you can find out the various relationships. So now let's go on to the acceleration relationship. So quickly, I'll do the acceleration relationship. So it's an extension of this, but we have more components. So still we have to relate B and A. We have to make the relationship between B and A. Why? Because we know some information of A and B, right? So as I kept writing, there is a normal component and there is a tangential component. So what we know here, I'll just write it, okay. So this is, what is this one? The normal component. So we can write it as omega square L RBA. Let me write it for the moment as RBA, and this we write it as RBA, right? Okay, so we can continue this one. So we know what is RBA. RBA is L cos theta I sin theta j, and plus alpha k cross, same thing here. Okay, so now you have, if you want, I'll start writing the, in terms of ij, what is AB? So B is only having rectilinear motion in the y direction. So I can write J here. And similarly, AA is having horizontal motion. So given the acceleration of A, so we know that it is AAI. And we have here omega L cos theta I, omega square L sin theta J. And then we'll continue alpha L cos theta J minus alpha L sin theta I. And we can relate it, I component is nothing but AA minus omega square L cos theta minus alpha L sin theta. And then we also have the relationship for J, and this is, what is that? Then it is simply minus omega square L sin theta. And then there is another term here, plus alpha L cos theta. Okay. And so we have two relationships here, two equations. So what is that which we can solve for? How many unknowns are there? Assuming that the acceleration of A is given to us. So omega, we have solved it in the velocity analysis. And then what are the two unknowns then? There is a alpha here and there is a AB here. So using the first equation, you can solve for alpha, and substituting that here in the second equation, you can solve for AB. So you can solve for alpha and given A. So you can solve for alpha and AB given AA. Okay, you understand? So now you can do it. So let's draw the acceleration diagram. So the acceleration diagram will be like this. So this is acceleration of A. Let's assume that it has been given to us. And what else? So we know that there's a normal component here, which is directed in this direction. So this is AB, the normal component, which is omega square L. L is the side AB. And then what else? Let me just try to. And to this, we have to add the tangential acceleration. So the tangential acceleration will be, obviously, will be perpendicular to that. And you know that I have to draw in this direction so that it will come in line with this one. So adding these two, adding these three, so this is, what is this? So it is L times alpha. Okay, right? So you can draw this. So what are the angles here? So the angles here, so this is parallel to AB. So that means that this is theta and this is perpendicular to AB. So with the vertical, it is theta. Okay, so you can make the equation, the same thing which you have done here can also be drawn there. For example, if you want to make the horizontal component equation, so this AA has to be equal to what? Omega square L and horizontal component, so cos theta, and then this is L alpha sin theta. So similarly, AB we can write as omega square L cos sine theta minus L alpha cos theta. So isn't it beautiful? So the vectorial, instead of going through the whole process of doing that, if you can draw the vectorial diagram, you can make the equation very fast. In fact, some of these things, of course, for example, the normal component may be very small. So somebody say that, okay, the whole thing is just starting from this. So then this may even drop, or even the tangential acceleration may be 0. So it depends upon what kind of problem you have. Okay. So whether you do this way or this way, so this is how you have to solve. So now let's look, I'll just indicate another very interesting problem, which seems to be trivial sometimes. Okay, which is so if you have a disk here, so, and then obviously the center point here, let us say it has some velocity given to us, and then obviously it is rolling down in this. Yeah. So I'm just looking at another example. So a very interesting example. Okay. Yeah. So I'm looking at another example where a disk is rolling on the ground and with some velocity here and angular velocity here. And so, of course, you know that omega is V by R. So if R is the radius here, can you prove it? So it looks very trivial, right? Looks very trivial. How do you prove that omega is equal to V by R? So from our kinematic considerations and rolling on ground, so let me add a qualifier without slip. So that means that if there is a point A here and another point B, which you take here, B on the ground, and A is the bottom point of the disk. So if they are rolling, so that means that if there is without slip means what? So that means that this point A is not having any relative motion with B. So it is not slipping. So A doesn't have any relative motion with B. So the thing here is that relative motion of A with B as far as velocities are concerned. Remember, the acceleration may be there. I'll come to that later. So the velocity of A and B in a horizontal direction is 0. Because ground is horizontal and A is rolling. I mean, the point A, which is the bottom point of the disk, is not going to have any relative motion with respect to the ground. So what does that mean? So what it means is that velocity of A is 0. The horizontal component of A is 0. Okay. So using that, so now we can really write down. So the velocity of A is velocity of C plus omega k cross so this k cross RAC is A with C is minus RJ, right? So that is VC, and this becomes IK cross J. So it is omega K R. Okay, so what does that mean? So if VA is 0, given a VC, which is in the horizontal direction, and this is also in the horizontal direction, Now you can see here that very clearly the omega is minus V by R. Why did I get negative sign for omega? It's because it's a clockwise rotation. Yeah, so what I was saying here is that again we go back to this relative motion equation, velocity relationships, and VA is VC plus omega K cross RAC. RAC is nothing but minus RJ. And then if I take the cross product, K cross J is minus I, and this is how it looks. So both are I components. So I can say omega is equal to minus V by R. So this negative sign here is because we have a clockwise rotation. Otherwise, if I want to include this omega here, then I should have put as a minus sign. Okay, I should have been putting a minus sign, then omega will turn out to be positive. So for this assumption. So this is the thing why omega turns out to be V by R from our kinematic analysis, because there's no slip. Okay, otherwise we say that, okay, the arc length of the disk, how much it has moved, should be equal to the horizontal distance. So that's what we did last time. And then we went on. Okay, I think I'll stop here. I have a few things, really very important things to talk to you.
Why this negative sign came once?
Yeah. Why negative sign is coming? Because when I wrote here, I didn't really use that I have assumed omega to be clockwise. But otherwise here, this is a very general expression. So here omega is assumed to be counterclockwise. Okay. So essentially the omega will turn out to be negative, saying that it is a clockwise rotation. And indeed it is so. Otherwise, if I have to put what all I have assumed there, then I should have put minus here. Okay.